This lesson is on inferential statistics. Inferential statistics makes inferences about populations using data drawn from the population. Instead of using the entire population to gather the data, the statistician will collect a sample or samples from the millions of residents and make inferences about the entire population using the sample. The first part of this lesson is testing a claim. For example, a researcher reports that the average salary of assistant professors is more than $42,000. So, when they sampled 30 professors, they found that their mean salary was $43,260 and that the standard deviation of the population was $5,230. Does this sample support the researcher's report? What we want to do is first find the z-score. The z-score is equal to x bar minus mu divided by sigma divided by the square root of n. Our sample mean is the $43,260. Our n would be the 30 professors. The population standard deviation, you're told, is $5,230. And the mean that we are testing is the $42,000. I should also mention that because the claim is that the salary is more than $42,000, and we found a salary that was higher than our claim, the $43,260, our data as of right now seems to support it, so we're going to go ahead and test it. Otherwise, if it ended up being less than the $42,000, we would have just rejected it from the start. And so we're going to run this test and see if it supports the claim. Using the formula, $43,260 minus $42,000 divided by 5,230 divided by the square root of 30. Our z-score rounded to the nearest hundredth is 1.32. Going back to the z-score table from last class, 1.32 would be 0.9066. That means that for our curve, 1.32 standard deviations above the mean, this area under the curve would be 0.9066, and that means that everything above 1.32 would be 1 minus 0.9066, which would be 0.0934. This means that at a z-score of approximately 1.32, it was about 9.34% probable to get a sample with a mean of $43,260 or above. Well, now going back to our claim, are we going to reject the claim that was made, or do we fail to reject the claim? How do we determine what the cutoff is? So before performing a study, a researcher actually has to first decide at what percentage or probability is an event considered to be significant. Typically, we use 1%, 5%, or 10% as our cutoffs. The second part of our lesson is on confidence intervals. A confidence interval is a range of values so defined that there is a specified probability that the value of a parameter lies within it. In other words, it's just a range of plausible values for our unknown parameter. A confidence interval is equal to the sample value plus or minus some random error. Our formula for confidence intervals for a sample mean would be the following: x bar plus or minus z crit times s divided by the square root of n. This is essentially just the random error. What is the standard error? So the standard error would be sigma divided by the square root of n, or s divided by the square root of n. Sigma and s both represent standard deviation. Sigma is the population standard deviation, and s is the sample standard deviation. The standard error tells you how far your sample statistic, like the sample mean, is deviating from the actual population mean. And so, of course, if we have a larger sample n, we have a smaller standard error. In order to have some kind of confidence interval, we want to identify what level of confidence we want. In the second column that you notice here, we have levels of confidence. A 68% level of confidence would be a z-crit of 1.0. A 99.7% confidence interval would be a z-crit of 3.0. My hope is that these numbers are familiar to us. In our lesson about normal distributions, we talked about the empirical rule. And then in our standard normal distribution, we talked about z-scores. That's all related to what we're doing here. My hope is that when you see 1.0 as our z-crit value, one standard deviation above and below the mean would capture 68% of the area under the curve. So if we want a 68% level of confidence, we would use a z-crit of 1.0. If we wanted a 99.7 level of confidence, we would use a z-crit of 3.0, which again was capturing 3 standard deviations above and below the mean. The most commonly used z-crit, and the one we're going to use for the purposes of this class, would be a 95% level of confidence, which is a z-crit value of 1.96. Example 1. A sample of 400 adults was asked the average time spent watching television each weeknight. The mean time was 68.4 minutes with a standard deviation of 20.9 minutes. Determine a 95% level of confidence for the population mean and interpret its meaning. Just as a reminder, this lesson is on inferential statistics. So my goal is to take these 400 adults as a sample and use this to make an inference about a population. I want a 95% level of confidence of what the true population mean would be for the watch time of television each night. So because I'm asked for a 95% confidence interval, I'm going to use the formula x bar plus or minus z-crit times the sample standard deviation divided by the square root of n. The 95% confidence interval means that I'm using a z-crit value of 1.96. Reading over my actual problem that I'm given, the sample mean was 68.4. The sample standard deviation was the 20.9 minutes, and the total number of adults that were sampled was 400. And that leaves me with 68.4 plus or minus my random error of 2.0482, and giving me an interval of 66.3518 to 70.4482. So I'm going to conclude that we are 95% confident that the mean time of all adults watching television each weeknight is between 66.4 minutes and 70.4 minutes. Example 2. A sample of 224 students show that they attend an average of 2.6 school athletic events each year with a standard deviation of 0.7. Determine a 95% confidence interval for the population mean and interpret its meaning. Again, we have another confidence interval we want to find using the formula x bar plus or minus z-crit times the sample standard deviation divided by the square root of n. Our sample mean, we found an average of 2.6 school athletic events, plus or minus a 95% confidence interval is a z-crit of 1.96. The sample standard deviation was 0.7 divided by the square root of the 224 students. Rounded to the nearest hundredth place, I find a confidence interval of 2.51 to 2.69. Therefore, we are 95% confident that the mean number of student athletic events attended by all students is between 2.51 and 2.69 events. In number 3, we have 2 different ways that data was collected. In letter A, we have 600 students were polled and 57% of them are voting for student A for ASB president. And we're asked to use a 95% confidence level to determine the margin of error and the confidence interval for the population proportion that are likely to vote for student A. Whereas in letter B, we have 600 who were asked how many hours they spend doing homework each night. We find a sample mean with a standard deviation, and we're asked to, again, use a confidence interval to determine the margin of error and the confidence interval for the population mean. So what is the two different ways that we collected data in these examples? Well, for example A, just focusing on what is highlighted here, the data that we were collecting was a proportion or a percentage, whereas in example B, that's similar to the previous examples we have been doing, where we find a sample mean, or the data that's collected is from a mean of values. Of course, we're still able to come up with a confidence interval for a sample proportion. We would just have a different formula than for a sample mean. These are the formulas that you would use. It would be a sample proportion plus or minus z crit times the square root of p times 1 minus p divided by n. And the z crit plus or minus the square root of p times 1 minus p divided by n is just our margin of error. What I would like you to do at this point is actually go back to number 4 and using the correct formula, figure out what the confidence interval is for letters A and B. For letter A, the formula that you should have used is the formula for the confidence interval for sample proportion, whereas in letter B, you would have used the formula for a sample mean. Please go ahead and check your confidence intervals at this time. Lastly, what is the difference between testing a claim and finding a confidence interval? So these are two different ways that we can. Lastly, what is the difference between testing a claim and finding a confidence interval? So testing a claim is what we did first in this video. Testing a claim was using a probability to determine if a sample is statistically significant enough to change our thinking of a population. So first, a claim is made. In the example that we had, the claim was that the average salary of the assistant professor was more than $42,000. Then what we did was we found a sample. In this case, we sampled 30 different assistant professors randomly. Next, we would have to determine some kind of cutoff for significance, whether it's a 1% cutoff, 5%, or 10% cutoff. Generally, a 5% cutoff is the most commonly used. And then we would determine the probability of that occurring. Lastly, we would answer whether or not the sample was rare enough to refute that claim that was made. Whereas finding a confidence interval is stating with some level of certainty that we know where a population parameter will lie. So to do this, we would collect some kind of sample randomly. Then we would find an interval with some specified level of confidence. And again, the most commonly or widely used is a 95% confidence level. And lastly, we would make a statement about the population value of the parameter. There are 10 questions that follow on this assignment, so at this time, if you can please get started on them.